Welcome back, everybody. Give me a minute, let some people in. Okay, hope everyone's doing okay. Any questions before we jump on to chapter 8? No? Okay. Now, chapter 8 deals with a topic called nomenclature. Basically, just how to name compounds. Now, as we progress through the chapter, I've been kind of introduced it, kind of get you ready for naming these compounds. A quick reminder that there is on the course website a button on the far left called StudyMate. And StudyMate, in there you can use flashcards. There's a couple multiple choices of things you can do in there, but I think the most effective is the flashcard option, and that allows you to look at formulas and then name them, or you're given the name of the formula and then write the structure. Okay, so that's a good aid to help learning how to write compounds. Now, the main point about this nomenclature is, one, ionic compounds do not have prefixes. No, you won't see any di, tri, tetra, hexa, any of that sort, okay? Covalent compounds will have prefixes, hence carbon dioxide, carbon monoxide. Those have prefixes. Don't mix and match, okay? No prefixes for ionic compounds. Prefixes for covalent compounds. Now that brings you back to the point. Let me show you how it's tied in. Now, ionic compounds, you have to determine, is that compound ionic? Well, you got to go back and remember what the definition of an ionic compound is. That's a combination of a metal and non-metal. Well, then you say, well, what's a metal? Well, that pulls you back even further to the periodic table and using that stair step to determine whether you got a metal to work with, okay? And you see how it's all tied in. Now, not only that, we've been talking on the periodic table, the ions that are formed, be it negative and positive, and it's all related to them being metal or non-metal. So we're kind of bringing everything together little by little. I mentioned earlier that in the beginning, that chemistry in the beginning is like learning the language, and the elements are basically our letters, and we learned about them, okay? Then we learned about how these letters, what kind of change they can undergo. And now we're going to put those changes together to make compounds. And then we're going to learn how to name these compounds. And then eventually we're going to start talking about getting these compounds to react with each other. All right? So let us begin. So that's nomenclature. Name that compound. Either given the formula or you're given the name. You can go one way or the other. Okay, for simple atoms, obviously we give them the name. So sodium is the sodium atom, and neon atom, et cetera, et cetera. Okay, so all the elements we have to name, give it something atom, whatever that element is. Unlike the ions, right? The ions, we call those either cations or anions, either positive charge or negative charge. Now, earlier we said learn the names and where they are in the periodic table for at least the first 20. So that's from hydrogen all the way to calcium. And then we're going to add a little bit more, a few more, and we will be adding little by little. No, we're not going to do all 118 elements, but we're going to do the major ones that we're trying to work with. And these encompass probably about 90% of them, okay? So Ba is barium, okay? Co is cobalt, okay? I is iodine. We're going to be using copper quite a bit. Cu is copper. Fe is iron, okay? You might be tempted to say ferrous or ferric, or no, it's just iron. And then Pb is lead. Hg is mercury. Ag, which sometimes gets confused with Au, which is the next one. Ag is silver, okay? Whereas Au is gold. And probably I think what happens is they see the G and Ag and think gold, but that's not the case, okay? So silver is Ag, Au from Orium, Latin term Orium, means gold. Zn is zinc, Zinc. And then next line we have Sn, which is stannous. Now, stannous is probably the only one that uses two names, and that is stannous or tin, Tin, okay? In fact, you're probably familiar with this morning, probably you're brushing your teeth with fluorinated toothpaste. And if you look at the label of that toothpaste, you'll see either sodium fluoride or stannous fluoride, one of the two. Okay, so this one down here, we also call it tin, Tin, okay? Strontium is the next one, Sr. Then we got nickel, a bromine, chrome, manganese sometimes gets confused with Mg, which is magnesium. Okay, so totally different. And then we got Cd, which is cadmium. So these are the, to begin with, are some of the elements we'll be working with. All right. Now, as we know, as we've been talking about, ionic compounds are metal, a combination of metal and non-metals. Okay, so if you don't know what is a metal, go back and refresh your memory about that. It's very important here. See, all of these chapters we've been talking about are eventually going to be tied in together till we get to the actual chemistry and what's going on. Okay, and then covalent compounds, also known as molecular compounds, are a combination of metals only. Now, the first part of this talk will be basically dealing with ionic compounds, okay? Now, monatomic ions, remember we have the ions because, why do we want to know if it's a metal or non-metal? Because we know that metals form cations, positive charge ions. And we know that nonmetals form anions, negatively charged ions. Then they come in different magnitude with respect to the charge, either +1, +2, +3, or -1, -2, -3, okay? Now, it is the cation and the anion that are going to come together to make the compound. So when we put them together, we have to know the respective charge, so we have to be able to put them in the correct ratio, okay? In the correct ratio. All right, so monatomic ions are singly charged ions. We calcium chloride, so on and so forth. But we also have polyatomic ions. Now, which ones am I talking about? Well, go to the periodic table. Notice here we have on the far left corner a table labeled most common polyatomic ions. These most of the time, majority of them are covalent compounds, but they're bonded together such that overall they have a net charge to them, which makes them ions. Okay, I repeat, a lot of these are covalent compounds, but they're put together in such a manner that they end up with a overall charge. So if we look at an example of, let's say, this one, NO3, it has its own very specific name. That's called the nitrate. So it's a nitrogen with 3 oxygens bonded around it, but it has an overall charge of a -1. Okay, that's called the nitrate. We don't change the names to call it nitrogen trioxide, no such animal. It is called nitrate. Another one, which is basically just minus an oxygen, is the nitrite, ITE. And notice a little trend here. We start off with nitrogen, That's nitrogen, right? We know that nitrogen is a group 5 element, and when it becomes an anion, it picks up 3 electrons, and we change the name to nitride. So names are very important here because it tells us how to put the structure together if we're given the name. So we start off with nitrogen as the element. If it's just nitrogen all by itself and it picks up 3 electrons, it is called nitride. Now, what happens is nitrogen can form compounds with oxygen, specifically 3 of them, and that's where they become nitrate, ATE, not IDE. All of the IDEs are the single nonmetal element. So oxygen becomes oxide, nitrogen becomes nitride, phosphorus becomes phosphide, just a single element. When you start seeing the ATE and the ITE, think about that element with bonded oxygens around it, okay? Look at sulfur, similar thing. We have S for sulfur. And it's in group 5, right? Group 6. They will pick up 2 electrons and form sulfide ion. Okay, sulfide, much like the nitride, the single element with, it's an anion now, but then bonded with it is oxygens, and we create what is called a sulfate. And specifically, sulfur has 4 oxygens bonded to it. The overall moiety has a -2. It's an ion, okay, specifically an anion. If it has 3 oxygens, it's called sulfite, okay? That is the name for these polyatomic ions. If we need more than one, we don't add the elements, we add a parentheses around it. So if we take nitrate, and for whatever reason, we need more than one, we put a parentheses and a subscript X, where X can be something more than one, 2, 3, 4, whatever you need. Because we're going to learn that when we put these ionic compounds together, we have to add enough cations, add enough anions to equal 0 overall. So end up with a neutral species. All right, so those are the polyatomic ions. And we'll be using them quite a bit. All right. Up to this point, I've been using the term, bear with me one second. Sorry about that. I had a cat over here making too much noise. Okay. Oxidation state. Don't get too worried about this term. It's just a fancy name for the charge. I've been talking about what kind of charge an ion has, okay? Plus or minus, okay? And this looks, that using the term charge is good when we're dealing with ionic compounds, because ionic compounds have a full-fledged negative or positive charge, right? When we deal with covalent compounds, they don't have a full-fledged negative charge. For example, let me give you a quick example. If we look at, just say sodium chloride, okay, color a little bit. We know that sodium, when it's an ion, has a full-fledged negative, and the chloride has a full-fledged, full-fledged positive for sodium and full-fledged negative for a chloride. Okay, we put them together to generate or create the formula of sodium chloride. So when we talk about the charge, that makes sense. However, when we're dealing with, let's say, carbon dioxide, these are covalent compounds. They don't have a charge. And so the term oxidation, they have a partial charge, if you recall. Remember, the charge the bond has a partial negative and a partial positive, okay? And so we can't really talk about having a full charge like we do with ionic. So to encompass both covalent compounds and ionic compounds, we utilize the term oxidation state. All right, so the oxidation state of sodium is a +1. For the chloride, it is a -1. In this example, for carbon, we don't really know, we have to calculate. But we do know that all the oxygens, be it covalent or being ionic, always have a -2 charge, and there's 2 of them. So we have a -4 charge overall here for the oxygens, and the carbons, we don't know what it is. So we can very quickly generate this very simple algebraic equation where C represents carbon minus 4, which is the total charge of all of the oxygens, equals 0. So that tells us right away that the charge, what we've been calling charge, is a +4 for carbon under this state. But it's not a full charge, so we talk about oxidation number. So the oxidation number of carbon in this format is a +4. The oxidation of oxygen is a -2 as normal for a covalent compound or an ionic compound, -2. Okay, so I'll be switching over to the term oxidation number. Okay, when we put them together, okay, the charge has to equal 0. All right, so we talked a lot about charges and what they have as far as where they're at in the periodic table. Okay, now a lot of the elements, let me restate that. There are 16 elements that have a fixed charge. Okay, let me repeat that. There are 16 elements that have a fixed charge. You know their charge 100% of the time. That means all the other metals have a variable. For example, copper can exist either with an oxidation number of a +1 or an oxidation number of a +2. It varies. So which ones do we know 100% of the time? Well, I directed to the periodic table. Okay, and you can mark up your table as follows. We know that all the metals in group 1 will have 1 valence electron, correct? Everybody agrees on that. That's what our model shows. Lithium, sodium, potassium all have different total number of electrons, but they all have 1 valence electron in the outermost energy level, okay? Second of all, they're all metals. And being all metals, they will lose that 1 electron. So everybody here that are highlighted in yellow will have a +1 charge. So there are 6 elements, specifically metal elements, that all have a +1 charge when they become ionized. Their oxidation number is a +1, okay? Everybody in group 2 has 2 valence electrons. And so there are 6 more elements that you know 100% of the time what their oxidation number would be when they become ions. Everybody in that second column will have a +2. So it gives you a total of 12 elements. And now I'm going to give you 4 more. Aluminum is number 13. Okay. 100% of the time, number 13, aluminum will always have a +3 charge. Zinc, which is diagonally to aluminum, will always have a +2 charge. Silver will always have a +1 charge, and CD cadmium will always have a +2. So those 4 plus the 12 of group 1 and group 2 give you 16 elements. I call them the sweet 16, so to speak, because those guys have a constant known oxidation number. It doesn't change. That means everybody over here, everybody else, their oxidation number varies. And that's important to know because that determines whether we're going to put an additional name to them, given an additional symbol in their name to distinguish the different parts, different types. For example, there are two forms of copper ion, oxidation number +1, oxidation number +2, okay? One of these has a green color, one of these has a nice blue color. As a child growing up in Superior, Arizona, which is an hour drive from here, east of here, there used to be a lagoon that we were supposed to play in, but, you know, being kids, we played there anyway. And I was fascinated by the water along the edge. The water was a blue, dark, very dark blue color, very beautiful. We used to think we were in the, quote, ocean, you know, Arizona boys in the ocean, right? Didn't know what that was, but it was a blue color. Later on, as a chemist, I found out that that blue color was one of these ions, and in high concentrations cause a lot of problems. In fact, over the years, I did research the data for a lot of copper mining towns here, Superior, Miami, Globe, Morenci, Kearney. As on a per capita basis, these communities, mining communities, have a higher than normal, higher than average cancer rates due to all the heavy metals and so forth that are caused by the mining. Now, these are just two, but there's all kinds of other metals that come out. Anyway, so there, all these other ones I highlighted in yellow have a variable oxidation state. And how do we distinguish between them? We utilize Roman numerals, okay? Now, I emphasize something here. Don't confuse those Roman numerals with the Roman numerals on top of the group. A totally different type use of Roman numerals, okay? Totally different. These Roman numerals that are next to the metal represent the oxidation state of that particular metal. You'll see that here. Hopefully a little clearer in a moment. All right, let's go back. And that's what the last entry here has. Other elements have a variable charge. Yeah, some of them can vary from a charge from a +1 all the way to a +9. Yeah, quite a bit. We know, again, just a recheck, is that cations are formed from metals that lose electrons, okay? And we also learn by using the Roman numeral A, or the A elements that corresponded to their corresponds to their respective oxidation numbers. So group 1, group 2, group 3 always have a +1, +2, +3 respectively, okay? For the metals, I talked to you about zinc and cadmium, and silver always have a +1, and zinc and cadmium always a +2. All right, there's 60 of them that have a constant oxidation number. That means that all the other metals can vary, like I stated, anywhere from +1 to +4, okay? And you might ask, well, how do we know which one it is? Well, when we start writing compounds, or when you're given compounds, you will always know one or the other. Either you're going to know the charge of the cation or the charge of the anion, the oxidation number. You're going to know one or the other. And you also know that when you put them together, they're going to be equal to 0. And so with that in mind, you can calculate what the oxidation number is for the other metal. For example, let's take a very generic example. All right. Before I proceed, let me back it up. I forgot to mention this. I did tell you about the charges of the metals, but what I did not share with you was for the anions, right? Now, we just told you all the charges for the metals, right? The ones that we know are constantly 100%, and telling you that everything else is variable. What about the anions? Well, I'll tell you what. Nitrogen and phosphorus always will have a -3. And then everybody in group 6 always will have a -2, always 100% of the time. Then all the halogens always have a -1. And so you know here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 anions that you know 100% of the time their respective oxidation number, okay? Be it in ionic compound or covalent compound, it'll be the same, all right? So you got that number of nonmetals, 16 metals, you know 100% of the time, and that means that all these other guys and vary. And so how do we use that information? Well, the way I'm going to do that, I'm going to generate a hypothetical compound. Right. So I'm going to take the letter M to represent some generic metal. Don't really care what it is. It's just M. But we don't know, and it's not one of the metals that we have a constant or 100% know the oxidation number. Some metals is variable. So we're going to say letter M, and then we're going to bond it to, let's say, oxygen. So we have some metal bonded to oxygen, and we need to calculate the oxidation number for the metal. All right, no problem. What do we know? This whole overall charge for this compound is 0, okay? Oxygen, we know, is in group 6. Now, be it in ionic form or be it in covalent form, it will always have a -2 charge, okay? Or oxidation number. That's good, and we only have 1, so we can simply put a -1. That means we've got this very simple algebraic equation, M minus 2 equals 0. What must M equal to? What is the value for M given this? Oh, let me redraw that over here. What must M be? What is the value of M given M minus 2 equals 0? Solve for M.
2.
Exactly, 2, you're right. Plus 2, -2 equals 0, right? Plus 2, -2, that definitely equals 0. And so that means that this metal, whatever it is, and I gave it generic form, has to have an oxidation state of a +2, because we know that oxygen has a -2, and that equals 0. Let's see how we work that. All right, let's reverse it now. All right, let's figure out something else. Let's do calcium X. Okay, X, it could be anything, any anion. Well, how do we figure that out? Well, what is it we do know? We know that this overall charge for this molecule here, whatever it is, has to equal 0, it's neutral, okay? We know that calcium, we find it on the periodic table, is group 2, always has an oxidation number of a +2, right? And then we have plus X. So what do we have here? Again, as we had a algebraic equation with M, we have one now with X. What must X be equal to? You can tell me that. So another way of saying X plus 2 equals 0, what is X? What number can X must be that you add 2 to give you 0? What must they be? Exactly, it has to be -2. There's no question. So here in this example, X exists in the -2 oxidation state because we know that potassium exists as a +2. Okay, and so that's the oxidation number of hypothetical compounds consisting of hypothetical cation and hypothetical anion. Okay, and knowing that the total number of cations plus the total number of anions must equal 0 for the majority of the compounds. I can give you a generic formula and say must equal the general charge of the overall molecule, because sometimes the molecules are not the 0. It could be a negative charge. Like you can do the same equation and take the sulfate, which has a -2, and calculate the oxidation number of sulfur right there. Okay, it is not -2 because this is sulfate. You got sulfur bonded to oxygen. So it's totally different. It's not sulfur by itself. It's sulfur bonded to oxygen. And you can use the same equation. Each oxygen's a -2. So you got sulfur minus -8 because each oxygen is a -2. You got 4 of them. And then the overall molecule charge is a -2. So what do you think the oxidation of sulfur is under these conditions? S minus 2 equal -2. Anybody want to take a guess at that? S is equal to 8 minus 2 is equal to 6. So the oxidation number of sulfur under these conditions is a +6 when it's in the sulfate format. Okay, so that general formula, total number of cations plus the total number of anions equal the charge of the molecule. With that general formula, you can figure out the oxidation number of any of the elements, but you have to know, obviously, either the charge of the cation or the charge of the anion. Okay, let us continue. All right, Roman numerals down at the bottom tell us the difference between the other elements that have a variable oxidation number. Things like copper. Copper 2 is written as copper Roman numeral 2. This is where the confusion hits sometimes, okay? Notice how it's written. Copper, parentheses, Roman numeral 2. That Roman numeral belongs to that metal, whatever that metal is. That tells you that the copper you're utilizing is a +2. That's what that is telling you right there, okay? And just like this one here, iron 3 tells you that that is the ion that the iron is in. It's a +3 charge. And lead, same scenario, Roman numeral 4 is telling you that, okay? Don't confuse those Roman numerals with the Roman numerals that are on top on the group of the periodic table. They have nothing to do with each other. It's a totally separate thing. They just happen to use the same format in describing either oxidation number or the group number, okay? All right. Now we know about anions, they lose electrons, okay? But in group 5, like the Roman product table, those single elements, nonmetals, will have a -3 charge. Not only that, remember this, the anions have a name change, okay? The anions. We get rid of everything and we add the suffix IDE. So group 5, you got nitrogen becomes nitride, phosphorus becomes phosphide, etc. In group 6, -2. In group 7, all the halogens, aka halides, halogens, halides, right? IDE have a -1. Now there's some variation, but we'll talk about that more for the halides. But fluoride always is -1. But for the most part, You may have saw the example we did last semester, excuse me, last chapter had BrO3, had bromine. Normally you think of bromine as a -1, but there are examples that they are bonded to oxygen. But when they're by themselves, I can overemphasize, when the halides are by themselves, that's a -1 charge. All right, and of course, group 8, noble gases, nothing's going to happen to them, okay? They're just stable and happy and not very reactive, at least in the Chem 130 world. All right, so we're going to take ionic compounds. We're going to begin by learning the formulas and then names for the compounds. Remember that ionic compounds are made up of ions, and the ions have a charge, which I'm changing the name to oxidation number, right? And when we put them together, we have to put them together with sufficient number of these ions so the molecule, the formula can equal to 0. Now the polyatomic ions, which are on your product table, okay, these we keep together as a group, as entities, and we don't change the name. That's important, okay? I've seen it happen numerous times, but don't do this. For example, NO3 -1. That species is called nitrate. People have tried to name that nitrogen trioxide. That is not the correct name. The NO2 is nitrite, okay? The hydroxide is the OH. That's called hydroxide. It's not oxygen, hydrogen, or something of some sort. It is a specific name. Also, point number 2, we don't take them apart, okay? If we need to add, let's say for whatever reason, we need 2 nitrates, okay? We need 2 of them. Well, it will be incorrect to do this, NO6. I have no idea what that is, but it's not nitrate. That is not right. If we needed more than 1, we use a parentheses. We put the NO3 inside the parentheses. And then let's say we need 2 of them, we put a subscript 2 to designate 2, 3, 4, whatever you need. If you only use 1, then you don't need the parentheses, okay? All right, let's see. Oh, all right, let's combine. You may get a question like this where they give you the element, sodium and nitrogen. Well, what you got to do first is take those elements and convert them to the ions. And we know that sodium is in group 1, and therefore that ion is a +1 charge ion, oxidation number +1. Nitrogen, okay, it is in a group 5, and then as it becomes an anion, it picks up a -3 charge. Okay, -3 charge. Furthermore, the anion gets a name change. The non-metal gets a name change. So if it goes from nitrogen, now we call it nitride, the ion, okay? Because you may need to name it, the final compound you generate. So we got a +1 for the sodium, -3 for the nitrite. We need 3 sodium ions to balance the -3 of the nitrite. So that 3 that I put in front of the sodium ion becomes the subscript for the formula as we put it together. So it becomes Na subscript 3, and the name written will be sodium, and the metal doesn't change, nitrite. Now, by default, not by default, by convention, when we write formulas, the metal is always written first, followed by the non-metal. Okay, so you'll always see the metal first, followed by the non-metal. I shouldn't say always, 99.99% of the time. All right, with that, we come up with the following formula. Na subscript 3 nitrite. And that is the correct ratio that these atoms come together to give you the formula. Okay. You won't see half numbers or decimal numbers. They're always going to be whole numbers. And if it's a 1, it's understood to be 1, and you don't need to put a 1 underneath the sodium, underneath the nitrite. It's understood there's 1, that's it. You don't need to put a 1 there. All right, so let's do some checks. And you're given these two, sodium and sulfur. Well, step number 1, convert to ions. Okay. Sodium, like we did in the first example, has a +1 charge. Sulfur, well, ionic form, we got to go to the periodic table and we'll find it that it is in group 6. Okay. And when it goes to ionic form, it picked up 2 electrons. It gained electrons, it's a nonmetal. So now that is the charge. Second of all, we have a name change. It went from sulfur to sulfide. Okay, keep that in mind in case you got to name it. So we got 1 sodium and 2 sulfides. So that tells us that we need 2 sodium with a +1 oxidation number to cancel out the -2 of the sulfide. So its formula becomes Na2 subscript 2S for sulfide. Okay, also known as sodium sulfide. All right, let's take a look at magnesium. Step number 1, convert them into ions. Okay, and the reason I tell you convert to ions, because that way it assures you that you have the correct charge and you can put them together correctly in the right ratio. Okay, and if you're familiar with what their charge is, you don't have to write it down like I'm doing here. Again, I always emphasize doing a systematic approach in what you in attacking these problems until you do sufficient enough that now you're familiar with what's what, and you can go directly to the answer. But first step here, magnesium convert to ions. Well, what do we know about magnesium? We're going to find it. It's on group 2. It's a metal. It's going to lose electrons. +2 charge, okay? Oxygen, like sulfur, is in group 6. It will gain 2 electrons because it's a nonmetal. Plus, oxygen now becomes name-wise oxide, okay? That name oxide is true whether it is ionic form or covalent form. And that's true with the sulfur, the other anions, whether they're being used in ionic form or covalent form, the name changes to the ID. So we got a +2 for magnesium, -2 for oxygen. We can simply put them together as a 1-to-1 ratio, and there we go. Okay, that's the formula. All right, potassium and phosphide, again, break them down into the ions. We've got potassium, which is in group 1. We got phosphorus, is in group 5. Which means it becomes ionic. Its oxidation number is a -3, okay? That means we need 3 potassium ions to balance the -3. So we got K3P, okay? And the name change goes from phosphorus to phosphide. All right, let's do one more here. All right, this is a little bit tricky, but let's work it through, okay? It seems tricky, but I think once you work it through, you'll see it wasn't as bad as it looks. All right, we got calcium, step 1, right? Make them into ions. We have calcium is in group 2. Its oxidation number is a +2. Nitrogen is in group 5. Oh, excuse me. And so it will have a -3. Okay. So up to this point, we've been able to just, either add enough cations to counter the anion or vice versa, depending what we're doing. pretty straightforward, kind of 1-to-1 relationship or 2-to-1, something to 1, right? Here's a different ballgame because we got calcium with a +2 and we get the nitrite with a -3. Now the question you got to ask yourself, how do I put them together such that they cancel each other out? I can't put them together as, let's say, in a 1-to-1, because overall I end up with a -1 charge, right? Because the calcium has a +2, nitrite has a -3. So what is left is a -1. So that won't work. Okay, so this won't work. So I need to find a way to put them together. Okay. And how to do that, I can answer that question by first answer this question. What do I need to do if I need to add a 1/3 plus 1/5? How do I go about attacking that problem? What do I need to do 1/3 plus 1/5 to add them? I cannot add them directly, right? Got two dissimilar numbers, but what is it that I need to do to 1/3 and to 1/5 before I can add them together? What do I look for? Anybody know? What do I look for when I'm trying to add these two fractions?
Common denominator?
You got it. We need a common number here, a common denominator for 1/3 and 1/5. Normally, we can just multiply the denominators, right? So it looks like the most common denominator could be 15 for these two numbers, right? So I need to multiply the 1/3 by some number. It gives me 15, so I gotta go 5 on top and the bottom. And for the next number, I can go by 3, top and bottom, okay? And so I end up with 5 15s plus 3 15s. Now I can add them to 8 15s and do whatever I need to do. But the point is, I had a common denominator. What is my common denominator with a +2 and the -3? Do I have a common denominator? Yeah, just like that decimal number. What would that be? Another way to look at this, how am I going to add 1/2 plus 1/3? What's my common denominator there? 1/2 plus 1/6. What's my common denominator there? Anybody know? What did I do down here in the first example? I just multiplied the denominator. Can I do the same thing down here with 2 and 3? Yeah. So my common denominator is 6. So what number can I multiply the -2 to give me a -6? Excuse me, what number can I multiply that -3 to give me a -6? Well, that would be 2, right? And what number can I multiply calcium to give me a +6? Well, that would be 3. See how that works? So that means that 3 is the subscript for calcium, and that 2 is the subscript for nitrogen, nitrite. So the formula becomes as follows. Calcium 3 and nitrite 2 nitrites, okay? That is the formula for calcium nitrite. And so when you have two dissimilar ions that you need to put together, find a common number, okay? Now there's a little something interesting here if you want to, let me show you the answer. There it is. I want you to think about this for a second. You didn't hear this on Chem 130, but think about it. Note the subscript of the nitrite. Isn't that the charge of the cation? Yeah. Note the subscript of the calcium. Isn't that the oxidation number of the anion? Yeah. Okay, so that may be an aid to help you when you put them together. That 3 becomes a subscript right here, and that 2 becomes a subscript right there, giving you CH3 and 2. Okay, but if you don't see it, no problems. find a common number like we did here for numerators. Okay, and then multiply it by a number to get to that common number that both share. Okay. Aluminum, this one's pretty straightforward. We know that aluminum has a +3 charge. Okay, and we know that the chlorides have a -1 charge, each one in group 7. So that means we need 3 chlorides for every 1 aluminum because of the oxidation number of each one. So our formula becomes AlCl subscript 3. There it is. All right, here's another one, zinc 2. Well, what do we know about zinc? Well, zinc is one of the sweet 16. It has an oxidation number always of a +2. And the iodides are like chloride up here. It's in group 7. It will always have a -1 charge. Okay, so that means I need 2 chlorides for every zinc. And so my formula becomes ZnI2. Okay, now we got one more here. Actually, a little more challenging here because now you're looking at this Roman numeral. Remember, that Roman numeral describes the oxidation state of that metal. And Roman numeral 2 tells you that copper is in this state because copper is not part of the 16. We don't know its oxidation number. It could be anything, one or two numbers, okay? So you have to be either told, like we did here with Roman numeral 2, or you can calculate it. I can show you that in a second. Oxygen becomes oxide, so we have a -2, okay? So we can put them together on the 1-to-1 ratio because copper is a +2 and oxide is a -2, so it simply is a 1-to-1 relationship, okay? And we have CuO. All right, one more. Let me clear this up a little bit. Here we have lead, Roman numeral 4, which tells you that that's a +4 oxidation state. The oxygen, like we did before, always has a -2, the oxide. All right, so that means that we need 2 oxides to balance the +4 of the lead ion. And so its formula becomes PbO subscript 2. Now, with respect to the name, let me do this. Okay, in the top one we have sodium sulfide. Getting the name correctly is important because it's not sodium sulfur, there's no such animal, but it is sodium sulfide because the sulfur is now the anion. And so here you could be given the name and from the name calculate or determine the formula in Na2S. Next one is magnesium, Mg, oxide. Occasionally, the Mg gets mixed up with Mn for manganese. Next one is potassium, phosphide. And then we got calcium, nitrite, and we got aluminum, chloride, zinc, iodide, And we have here now copper. We have to use a Roman numeral given. Copper, Roman numeral 2, and then O is oxide. Okay. Here we have lead, PB is lead, LEAD. We have to use the Roman numeral oxide. Okay. Notice for the other metals, we did not use the Roman numerals. They have to. Why? Because those metals belong to the sweet 16 category. Those are constant, exact oxidation states, and therefore do not require to have a Roman numeral because they only have one oxidation state. That's it. Everybody else can have a multiple oxidation states. All right. Also, you can see how you can start building up your database. Right now, we did sodium and sulfide, but you can very quickly do sodium and oxide, sodium and phosphide, sodium and nitrite, sodium and chloride, sodium and iodide. And we already did the oxide, but you do the same thing with magnesium and sulfide, magnesium phosphide, etc. You do the mix and match, okay? You're already up to maybe 400 or 500 different compounds you have access to. Okay, just with what we just started here. And, you know, we haven't touched all the metals that you can do. And so you can mix and match and just create a multiple of compounds with the structure and the name too. All right, so the important thing when you put them together, make sure you put enough of each ion so that the charges or the oxidation numbers cancel out to equal 0, okay? Because that's what happens with the majority of the compounds we put together. But keep in mind, the charge could not equal 0. If it's a polyatomic ion, it could equal -1, it could equal anything. -2, I shouldn't say anything, -2 or -3. Okay. Now, with respect to polyatomic ions, we have this here. We got to put together the magnesium and the OH. The fact that they give you OH and then a negative should flag to you and tell you, this sounds like a polyatomic ion. And so what you do is you go through the periodic table and you say, hey, do I have an OH negative? And sure enough, if you look right there, here you go, right there. OH negative, you got the hydroxide. So already you know the name. You don't change the name. Its name is hydroxide. If I need more than one of those hydroxides, I use a parenthesis. Okay? Well, to determine that, you first need to convert that metal that you're given and convert it to the ion. And so we know it's a group 2 ion, so it's a +2. And the hydroxide is a -1. So that means I need 2 to cancel the +2 for magnesium, which tells me what I do is I go ahead and put my parentheses, and then I just put a 2 there, okay? Because that's what's going to happen here. So I got very quickly put them together. Now, a reminder here. Once you put them together, don't bring along the charges, okay? I put the charges out here when you're separated, so I know how much of each to put together. Once I put them together, you leave the charges off, okay? All right, so that is the formula for magnesium hydroxide. There it is. All right, a little more interesting one in that you have PO4, which again is a good indication that you're dealing with a polyatomic ion, okay? And so it's a -3, and potassium has a +1. So I need 3 of them. I'm going to need 3 of them here. And because I got 3 pluses and a -3 on the phosphate. Okay, so there's my formula, potassium phosphate. Okay, here's another one. SO4 -2. Check the polyatomic ion table. You'll find it to be the sulfate. Okay, the silver is always a +1 oxidation state. And so we got a -2 for the sulfate, because from the polyatomic table, you'll see its name given to you. It is not sulfur tetraoxide, it is sulfate. Silver has a +2, so that means I need 2 silvers to counter the -2 of the sulfate, and I got as follows. Calcium nitrate, calcium, we know is a +2 ion. The nitrates are a -1. It's given to you right there. Okay, that means I need 2 of them. So I go ahead and put my parentheses there to show me that that's how many I need. And then I put them together without the charges, and I have calcium nitrate. All right, here we go with the Roman numerals, which tell me that I'm dealing with copper +2. And the CO3 -2 is the carbonate ion, polyatomic ion. So it's a +2, a -2. I can simply put them together in the 1-to-1 ratio. I don't need any parentheses, and there I go. I have that there. Okay, now, the thing about this is remember to use parentheses when you need more than 1 polyatomic ion. For example, that one and that one. When you only need 1, you just leave it alone. You don't need it. Naming wise, this is magnesium hydroxide. I believe this is the active ingredient found in milk of magnesia. Yeah. And then we have potassium phosphate, excuse me. There is a phosphite that's just basically 1 less oxygen, ITE, but that's not in our table. And then we got silver, sulfate. You know, we tend to eat a lot of sulfates. If you read the labels, you'll find a lot of sulfates, sodium sulfate, potassium sulfate in our foods, quite a bit actually. And then we got calcium nitrate. Okay, be careful, make sure it's nitrate, because if that 3 was a 2, it would be nitrite. Quite a bit of difference. And then finally, we got copper. Since we're using Roman numeral 2, we got to continue it. So it's copper. Include the Roman numeral 2 carbonate. It used to be that copper 1 and copper 2, along with the other ones, they used to use the IC, and OUS, and that was kind of ambiguous. And so all that was cut out. In fact, you may find it used sometimes on a lot of labels, but that's not the correct nomenclature. We use Roman numerals to distinguish, and that is governed by a international body of scientists and organization that looks at the names of compounds. It's called the IUPAC organization, and everyone agrees that this is the name of this compound and this is the name of that compound, and there's no ambiguity. There used to be a lot of ambiguity in the naming. Everybody was naming things differently. Some things remain the same, like water, H2O, just by convention, because technically its name should be dihydrogen monoxide, H2O, the way it's written. Okay, so yeah, you might Google that. You see what you can find. Dihydrogen monoxide. You can read about all the hazards of dihydrogen monoxide in the world. All right, where are we at? Okay. You know what? I got an appointment at 5:30 telephone appointment. So what I need to do, I'm gonna have to cut it here on slide number 12. Okay. And we will finish this chapter on Tuesday next week. This is number 12. And you're only one slide behind my other section. And then, yeah, next Tuesday, we'll finish this and jump in the next chapter, chapter 9, which deals with acids and bases. Another fairly short chapter, doesn't take too long to go through. So we should be done with the next group of chapters for sure next Thursday. Okay? Let me stop.